It is not possible to hook up three single-phase transformers in a closed delta with a 480 volts primary and a 240 volts delta secondary with a neutral. Single-phase transformers have two windings, a primary winding and a secondary winding. The primary winding connects to the power source and the secondary winding connects to the load. In a closed delta connection, the secondary windings of the transformers are connected in a closed loop without a neutral connection. While it is possible to connect three single-phase transformers in a closed delta, the primary and secondary voltages are limited. For a closed delta connection with a 480 volts primary, the secondary voltage would be 277 volts, not 240 volts, and it would not be possible to create a neutral connection. On the other hand, for a closed delta connection with a 240 volt secondary, the primary voltage would be 138.6 volts, not 480 volts, and again, it would not be possible to create a neutral connection. To achieve a 480 volts primary and 240 volts delta secondary with a neutral, you need to use a three-phase transformer. A three-phase transformer has three primary windings and three secondary windings connected in a delta or Y configuration. In a delta-delta connection, the primary windings are connected in a delta, and the secondary windings are connected in a delta, providing the desired voltage levels and a neutral connection if properly derived from the delta secondary using a zigzag grounding transformer. To understand why a single-phase transformer configuration won't work, it's important to delve deeper into the principles of delta connections. In a delta connection, the voltage across each winding is the same, but the current is divided among the windings. When using single-phase transformers in a delta configuration, the voltage ratio between the primary and secondary sides is determined by the turns ratio of the individual transformers. Firstly, consider the voltage relationships. With a 480 volts primary and the desired 240 volts secondary, the turns ratio would need to be 2:1. However, in a closed delta configuration with single-phase transformers, the secondary voltage is not simply half of the primary voltage. The voltages in a delta connection are related by the square root of 3, which is approximately 1.732. Secondly, if you apply 480 volts to the primary side of single-phase transformers connected in a delta configuration, the secondary voltage will be 480 volts divided by 1.732, resulting in approximately 277 volts, not 240 volts. This is because the delta connection inherently changes the voltage relationship. Thirdly, creating a neutral connection in a closed delta configuration with single-phase transformers is problematic. A neutral connection typically requires a center tap or a specific winding configuration that provides a reference point for balanced loads. In a closed delta, there is no natural center tap or neutral point. Fourthly, to establish a neutral, you would need to introduce additional components such as a zigzag grounding transformer. However, this defeats the purpose of using a simple closed delta configuration and adds complexity to the system. Fifthly, using a three-phase transformer simplifies the process significantly. A three-phase transformer is specifically designed for three-phase power systems and can provide the desired voltage transformation and neutral connection without the limitations of single-phase transformers in a closed delta configuration. Sixthly, the delta-delta connection in a three-phase transformer allows for a direct voltage transformation between the primary and secondary sides while maintaining the delta configuration. This means you can achieve a 480 volts primary and a 240 volts delta secondary with the correct turns ratio. Seventhly, to create a neutral connection with a three-phase transformer in a delta-delta configuration, a grounding transformer, such as a zigzag transformer, is typically used. This transformer creates a neutral point that can be connected to ground, providing a reference for balanced loads and fault protection. Eighthly, the zigzag transformer works by connecting each of its windings in a specific way to provide a low impedance path for zero-sequence currents, which are associated with ground faults. This allows the system to detect and respond to ground faults effectively. Ninthly, attempting to force a neutral connection in a closed delta configuration with single-phase transformers can lead to unbalanced voltages and currents, potentially damaging the transformers and connected equipment. It is crucial to adhere to the correct wiring configurations and voltage relationships to ensure safe and reliable operation. Tenthly, in summary, while it is possible to connect single-phase transformers in a closed delta, it is not suitable for achieving a 480 volts primary and 240 volts delta secondary with a neutral. A three-phase transformer is the appropriate solution for this application. Now, let's examine the specific voltage and current relationships in more detail to understand the limitations of the single-phase transformer configuration. In a delta connection, the line voltage is equal to the phase voltage, but the line current is equal to the phase current multiplied by the square root of 3. This means that the current in each winding of the transformer is different from the current in the lines connected to the delta. When using single-phase transformers, this current imbalance can lead to uneven heating and reduced efficiency. Additionally, the absence of a neutral connection in a closed delta configuration can create challenges for load balancing. In a balanced three-phase system, the neutral conductor carries very little current, as the currents in the three phases cancel each other out. However, in an unbalanced system, the neutral conductor can carry significant current, which can lead to voltage drops and overheating. Without a neutral connection, it is difficult to mitigate the effects of unbalanced loads, which can further exacerbate the current imbalance in the delta connection. Furthermore, consider the implications for grounding and fault protection. In a grounded system, a ground fault will cause a large current to flow through the ground conductor, tripping a circuit breaker or fuse and isolating the fault. This provides protection for personnel and equipment. However, in an ungrounded system, a ground fault may not be immediately detected, and the voltage on the unfaulted phases can rise, potentially damaging equipment. The absence of a neutral connection in a closed delta configuration makes it difficult to establish a reliable grounding system, which can compromise safety and reliability. To illustrate the difference between single-phase and three-phase transformer configurations, let's consider a practical example. Suppose you have a three-phase load that requires 240 volts delta and draws 100 amps per phase. If you attempt to supply this load using single-phase transformers in a closed delta configuration, you would need to provide 277 volts to the secondary windings to achieve the desired 240 volts line-to-line voltage. However, this would require a different turns ratio for the transformers and would not provide a neutral connection. Moreover, the current in each winding would be different from the line current, potentially overloading the transformers. On the other hand, if you use a three-phase transformer with a 480 volts delta primary and a 240 volts delta secondary, you can directly supply the load with the correct voltage and current levels. The three-phase transformer is specifically designed to handle balanced and unbalanced loads and can provide a neutral connection for grounding and fault protection. In addition to the technical limitations of using single-phase transformers in a closed delta configuration, there are also practical considerations to keep in mind. Firstly, three-phase transformers are readily available and are designed for three-phase power systems. They are manufactured to meet specific standards and are tested to ensure reliable and safe operation. Secondly, single-phase transformers are typically used for single-phase loads such as lighting, appliances, and small motors. They are not designed to handle the demands of a three-phase system. Thirdly, attempting to adapt single-phase transformers for a three-phase application can be costly and time-consuming, as it requires careful planning, wiring, and testing. Fourthly, it is generally more cost-effective and efficient to use a three-phase transformer for a three-phase load. Furthermore, consider the implications for maintenance and troubleshooting. Three-phase transformers are typically easier to maintain and troubleshoot than custom-built configurations using single-phase transformers. Three-phase transformers have standardized components and wiring diagrams, which makes it easier to identify and repair problems. Single-phase transformer configurations, on the other hand, may require specialized knowledge and tools to diagnose and resolve issues. Moreover, The use of non-standard configurations can complicate the process of obtaining replacement parts and can increase downtime. In summary, while it may be tempting to try to adapt single-phase transformers for a three-phase application, it is generally not a practical or cost-effective solution. Three-phase transformers are specifically designed for three-phase power systems and offer numerous advantages in terms of performance, reliability, safety, and maintainability. To further illustrate the advantages of using a three-phase transformer, let's consider the different types of three-phase transformer connections. The two most common types are delta-delta and delta-Y. In a delta-delta connection, both the primary and secondary windings are connected in a delta configuration. This type of connection is typically used when a neutral connection is not required on either the primary or secondary side. It is relatively simple to implement and provides good voltage regulation. In a delta-Y connection, the primary winding is connected in a delta configuration and the secondary winding is connected in a Y configuration. This type of connection is commonly used when a neutral connection is required on the secondary side. The Y connection provides a natural neutral point which can be grounded to provide a reference for balanced loads and fault protection. The delta-Y connection also offers advantages in terms of voltage transformation, as the voltage on the secondary side is equal to the voltage on the primary side divided by the square root of 3. This allows for a step-down or step-up voltage transformation without the need for additional transformers. When selecting a three-phase transformer, it is important to consider the specific requirements of the application, including the voltage levels, load characteristics, and grounding requirements. It is also important to choose a transformer that is rated for the appropriate kV amps and frequency. Moreover, it is crucial to ensure that the transformer is installed and maintained in accordance with the manufacturer's recommendations and applicable electrical codes. In addition to the technical and practical considerations, it is also important to be aware of the relevant safety standards and regulations. Electrical work can be dangerous, and it is essential to take precautions to protect yourself and others from electrical shock and other hazards. Firstly, always de-energize the equipment before working on it. Secondly, use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. Thirdly, follow the applicable electrical codes and standards, such as the National Electrical Code, NEC. Fourthly, if you are not qualified to perform electrical work, hire a licensed electrician. Furthermore, be aware of the potential hazards associated with transformers, such as high voltages, flammable materials, and magnetic fields. Keep the area around the transformer clear of obstructions and ensure that the transformer is properly ventilated to prevent overheating. Inspect the transformer regularly for signs of damage or deterioration, such as cracks, leaks, or corrosion. If you notice any problems, contact a qualified electrician to investigate and make repairs. In conclusion, while it may be possible to connect single-phase transformers in a closed delta configuration, it is not a suitable solution for achieving a 480 volts primary and 240 volts delta secondary with the neutral. A three-phase transformer is the appropriate choice for this application, as it provides the desired voltage transformation, neutral connection, and performance characteristics. Remember to always prioritize safety and follow the applicable electrical codes and standards when working with electrical equipment. It's important to remember that the NEC, specifically Article 450, covers transformers. Firstly, Part 3 covers overcurrent protection, noting the requirements for transformers over 600 volts and those 600 volts or less. Secondly, Article 450.3 covers overcurrent protection for transformers over 600 volts and dictates the primary and secondary protection requirements. Thirdly, for transformers over 600 volts, the primary overcurrent protection device shall be set to protect the transformer. Fourthly, the NEC provides tables such as Table 450.3a, which gives the maximum overcurrent protection settings for transformers over 600 volts. Fifthly, Article 450.3b covers the overcurrent protection for transformers 600 volts or less. Sixthly, This section provides different rules based on whether the transformer primary current is more than 9 amps or less than 9 amps. Seventhly, for transformers with a primary current of more than 9 amps, the overcurrent protection device shall be rated or set at not more than 125% of the rated primary current of the transformer. Eighthly, Table 450.3b provides the maximum rating or setting of overcurrent protection for transformers 600 volts or less. Ninthly, for transformers with a primary current of less than 9 amps, 450.3b provides different requirements, allowing higher percentages for overcurrent protection. Tenthly, the NEC also addresses the location and accessibility of overcurrent devices for transformers, ensuring they are readily accessible and properly labeled. Understanding and adhering to these NEC requirements ensures the safe and reliable operation of transformers and protects against potential hazards.